Hello everybody and welcome to my channel. In this video I want to get you excited about what's coming to Swift. Probably you have heard about memory ownership, something that it's coming and it's being discussed with Swift. I've talked a lot about it, to be honest, because I'm very excited about it. Pretty much as excited as I was with Swift concurrency, and I talk about that a lot. So in this video I want to tell you why you should care about memory ownership in Swift. And no, don't be afraid. I'm not gonna go super crazy and complicated and talking about all the ins and outs. I just want to show you how the code that you write today can be improved if we get a couple of the things that I hope they are coming soon to Swift. We all love Swift because of its optionals, enums with superpowers, but really what made Swift shine was its focus on value semantics. Yes, it still has all the OP baggage and we need to deal with that, and it's very useful sometimes, but value semantics is where Swift shines the most. And not only that, but they introduce value semantics in a way that you could still talk about mutability while keeping value semantics, and they all are a breeze to work with. The syntax is very nice, very intuitive. It feels like you're working with references, but not really. But sadly, that has a limit. So let's explore value semantics, mutable value semantics, and how memory ownership will help in the future. So here we are in Xcode, and let's first talk about what is value semantics. I mean, by now everybody that has been reading Swift for a while knows what value semantics are, but let's just do a quick recap. And let's start by the thing that it's a value pretty much on every language, a number. So here we have an original number, and now we can make another by assigning that number, right? If you do this on pretty much every language, if you now go to the other variable and increment it by 2, you don't expect the original to have changed because they are numbers, right? They are just like primitive values, right? Well, so it doesn't have primitive values per se, but it has value semantics. And an integer in Swift is just a struct like any other. And of course, it respects value semantics. So that's what the whole value semantics means. It means that you have values and not references. You have something that when you pass it around, it becomes independent from the previous copies. That's what it is. And in Swift, this is not only limited for numbers, like in other languages it only works because those are primitives. Swift doesn't have that. It works for pretty much every type that you want to make a value of. So we could change this and actually make it a string, right? And now we have another string. And here we can say world. And now if we print this, we again have the original not touched and the copy modified. Nothing new, nothing crazy, we're just exploring value semantics. It surprised to many of us at the start was, wait, arrays are values? How does that work, right? Like at the beginning, we all went a little bit, wait, what does that mean? But after so many years, we're all used to it. Like I even remember on the original days when Swift was just released, I think it was even a beta, like things were very early back then. Nobody was thinking about using it in production even. I was like, what is this thing? But the ones that were excited and we jumped on the train very quickly, we saw something that probably many of you don't know, which is like originally arrays didn't respect value semantics. It was kind of a bug, and you know it took a couple of mails to say no, yeah, we are gonna change that, and I think quickly they fixed it. But originally something that now we're very used to it, which is like you have an array and you're making a copy of it, so mutating the copy doesn't change the original one, and you have two versions of that array that have diverged. Originally that was not even the case, like arrays didn't respect value semantics in that sense. Thankfully for everybody that was fixed, quickly fixed, and now we have been living in value semantic land for a long time. But as I said, Swift doesn't have primitives, so these things, arrays, integers, strings, those are just structs. What does that mean? Well, it means that you can have value semantics on your own types. How do you make your own value types? Very easily. You just define a struct. We're all used to it. But a struct is not a class. It's not an actor. A class and actor are reference types. Structs, enums, tuples, all of that respects value semantics. So what does that mean? Well, again, it means that you can create an original value with some data. And then you can make a copy out of it. You can assign it. This assigning makes an implicit copy, which becomes important in a bit. And then you can mutate that copy, and still the original stays as it was. So we still have Josephine at age 16, and then we have Josephine Robinson at age 16. Very important, and this is a tool that we use constantly. You still need to use OOP in many places because many frameworks still need it, and reference semantics are still needed on very specific instances. But to be honest, if most of your code you have been using structs, you are on the right path. Most of the time, you don't need more than that. You can just have values and pass them around and make sure you don't have the spooky action at a distance that it's very scary and it gets very hard to maintain in big code bases. But as I said, this does not stop with the structs. You can also have enums, and enums in Swift are very powerful. So let's define here a new enum, points origin. We're gonna see the topic, but you can already see it, right? So the origin of the points can come from the headmaster, and there is only one, so we don't have to give it a name, right? Or we can come with the teacher, and you can give it a name. Or from a game of Quidditch, and which game it was? Well, the third or the fourth, right? So that's an enum, very powerful in Swift, and it respects the same things. You can say that the original value was given by a teacher. And then you made a copy and decided, oh, you know what? Well, it actually was done by the headmaster. And you can change the enum to point to a new value. And there you have it. You have two, the original was not modified, and the second is the headmaster. But pay attention, because these are not only value semantics where you pass things around and they get copied and you don't have the spooky action at distance. No, you can actually mutate them very similarly to how you just work with classes. The nice thing is that the language even has special support to perform these mutable semantics on functions. So let's see how the language brings this power of mutability into more places than just mutating a struct. If you have this function that receives a student and wants to give it a new name, and then here, what can we do? We can put the name to the new name. Well, that's not gonna work because we cannot mutate that, right? It's a let constant. Maybe we can just do what we did before. We can make an other and take the student, and now we can mutate the other, right? That should work. Now let's give this a go, and we have original student, Josephine, 16, and we want to change the name of Josephine to Charles. So if we run this, of course, it's not going to work. Like, we're not changing the original. Remember, value semantics. What you're passing here is just a copy. Even you're making another copy here, so you're just copying things all over and changing things. Yeah, this other will have changed the name, but that doesn't reflect outside. Swift brings, again, the mutable semantics into the language in a very elegant way. You can pass this as an in-out parameter, which then forces you to understand that and make sure you pass this as an in-out parameter. And now you are able to take that student that you are receiving and mutate it in place. This may sound obvious for people coming from other languages with everything is a reference, or even in C or C++, you're like, oh, that's passed by reference versus passed by value. Yes, it's very similar, but not really, because you're still passing a value. It's just that the compiler is able to give you a copy. You mutate the copy, and then the compiler puts that copy back where it came from. It goes in, gets mutated, and the copy gets back. It's basically a kind of sugar for if you wanted to return a new student, which many APIs do, and then assign it back. And again, the compiler can optimize this and actually do it by reference internally, but that's out of the scope of this video. But now if we run this, we actually see how Josephine has become Charles. That's very cool. But the language doesn't stop there. The language actually allows you to do something kind of special, right? We can make an extension, for example. We could just write it on the same place, but let's make an extension. And you can make a function for the anniversary that basically increases the age. But we're in the same situation here. Self is not mutable. Remember, a student is a struct. You cannot just mutate structs like that because they are values. But in the same way that you have inout to put on arguments for functions, you can declare the function mutating, which this is kind of saying inout self. right? That's it. Basically, these and these are very similar. They have kind of like very different syntaxes, but at the end they are doing the same thing. If in Swift you declared self as a parameter, which we don't, it's implicit when you put it inside a type, that's basically what you will do. You will do inout self. And these things become important when ownership comes into place, which we're getting there, I promise. So now you can do this and take the original and use the natural dot syntax to do the anniversary, right? And now we're gonna have Charles at 17. Cool. So you see how Swift has value semantics that are mutable and how nice it is on the language. But sadly, it still has limitations. It's not as nice to use in many cases. So let's explore those scenarios. Let's talk about how you define more realistic, more complex scenarios, right? So in this case, we have a school that has a name and it has a bunch of houses. And each house has a name, has alumni, and preceptor. Kind of like a complex nested structure. Now, if we go back to what we did before, we can try again to do the same thing, right? So we have an original, which is a school, obviously, it has to be Hogwarts. And then we have houses, which is Ravenclaw. I think I'm gonna play Ravenclaw when the Hogwarts game comes out, I'm pretty sure. And then we have some alumni, which is again Josephine at age 16. We can make a copy of this, right? Remember, we're making copies everywhere, like everywhere is a copy. And yeah, they are optimized, copy on write, all that stuff, all the cool stuff that you already know. But mentally, you need to think we're making copies, right? And how we can go and change the age of Josephine, right? Think about that. You can go very easily, like if it just was a class, right? Like it's very natural and easy to write. I go to the first house, I go to the first student, and then I increase his age by 10. And if I print the original and the other, we can see how both of them change. We have the original at age 16 and the other one at 26. But look at this, with dot syntax and subscripts, you are able to go and traverse the deeply nested structure and mutate it in place. That's very important because this is where the mutability comes into play. Like you can do these things and it's very nice, it's very easy. This works because you can treat dot syntax as making self mutable, right? It's very similar to what we did with the mutating functions, right? If you have mutating functions, you can just dot syntax them and you get this in place mutability. And also subscripts. Subscripts give you a view into part of the structure where you can actually change it in place, right? And there is some optimizations, there is some like coroutine stuff, pretty cool going on in there. That's the power of mutating functions, and it's the power of subscripts. Nobody else has the power. And that's where the problem comes. So let's imagine that we want to do this, just rewriting it a little bit. Let's just get this one and let's just remove this just for simplicity, because I mean, you understand the fact that one doesn't change the other, that's pretty clear now. But let's take this and let's see how this can get very verbose, right? It's too much. One line, yes, one-liners are very nice, but sometimes too tricky. And sometimes you don't know which index it is and you want to compute it and stuff like that, right? So the natural thing is that you are gonna want to make local temporary variables to manage the code a little bit better and make it a little bit nicer. So we get the first house, we get the first student, and now that we have the student, we increase the student age. All of this works. At every step, we are using subscript and dot syntax, and we are basically mutating the values. But as soon as you do this and you print it, you see that you haven't actually changed anything. As opposed to if you do the one that it's one-liner, you are actually able to change it. That's where the limitations start to pile up. You are not able to take values of a structure, of a deeply nested structure, of an array, because as soon as you do this, you are making a copy out of it, right? And then when you're mutating, it's the copy, which is what we want most of the time. But sometimes you have these deeply structures or arrays where you actually want to mutate in place, because keeping the indices around, it's a little bit of a pain. If we wanted to do this, now we have a copy of a student that works fine, right? But now we don't have any other way that just go back to this long line and now assign that student. And this will actually work, but why do I have to do this? But you could say, okay, Alex, well, just write it like this, and that's it, right? And yeah, you're right, and that's what we do most of the time. But there are other cases where you actually cannot do this that nicely. For example, imagine that we want to go through all the array of alumni of a house and actually increase their age. You could make a for loop. And now you want to do student age, right? Or even like we can call just the anniversary, because that's going to increase it by 1, right? But you cannot do that because you're trying to mutate a let constant. A let constant is because the student is a let. There is a trick that you can make this a var, right? And now this is a mutable thing. But again, this has been copied on every loop. On every loop, when we go through the array, we basically make a copy in the same way that we were doing here. So if we print the original, Josephine, it's still gonna be at 16. Another limitation of the mutable semantics in Swift. The limitations don't stop there. Like for example, have you ever had an optional that you wanted to mutate in place? Let's see how that looks. So let's bring back again the house. In this case, we are going to talk about Ravenclaw. We have a preceptor, which is George at age 20. But let's imagine that I want to check, if there is a preceptor there, increase its age, right? So you will do preceptor equals the house preceptor. And this is an optional, right? So we do an if let to unwrap that optional. And here we are again, preceptor anniversary. That's not gonna compile because it's a let. You can do again the trick and say it's a var, but that var it's a copy. We print the house, it still didn't change. It's still 20 years, not 21. And here, my friends, is where improvements on the memory ownership model can make the language shine even more. There are a lot of proposals going on right now on Swift Evolution about pitches, manifests, everything interconnected to each other. It reminds me a lot about the time where the concurrency was being developed. Swift right now is nice and easy to use because it takes care of a lot of these things, but the trick that it employs most of the times with value semantics is that it makes implicit copies. Well, tools are gonna come to allow us to control that, to basically disable this implicit copy behavior ad hoc when we want it, or even create complete types that are not able to be copied. So that means that copies are not going to happen on every assignment or when you pass things to a function. Like, we're going to have control over that while still keeping the defaults as nice as Swift makes programming. If you know Rust or C++ or other languages, you can see how many of these ideas are coming into place. Especially with Rust, we can see how the memory ownership model in there has inspired a lot of the things that we are like talking in the Swift evolution with memory ownership, borrowing, and all that stuff. So the model is going to be quite similar, I expect, but still making it nice with the syntax and improvements that Swift usually brings on the table. This is a topic that fascinates me because it's something that I've been wanting improvements for ages. Rust is an amazing language and it has very cool stuff that you can barely do in other places, but it also has a very, it's kind of tricky to learn, or like sometimes it's a little bit pedantic, so if we can have the nice things without getting to the extreme, I'm not sure we need to get to the extreme, but if we can get all those nice things in the nice package that Swift is, it's going to be exciting. It's the same as concurrency. I have so many things, it's so big, and I just want to share it a lot. But the point is that you are not here to talk about all of that. You're here for one thing. I promised you that I will make you care about memory ownership, and for that I need to show you how your real day-to-day code is going to improve drastically with just one of the things. Like, we don't need the whole ownership stuff, that's too complicated, right? You don't care about that. Please don't say that the language is going to be complicated. Ignore all of that. There is only one thing that I think you need to care about. So let me show you how these hypothetical improvements, remember, none of this is approved, the syntax is I'm just making it up, right? Hopefully it's going to be similar, but I'm just making it up. I think conversations are happening, so this is just a look at the possible future. And the future is uncertain, so don't take this as copy-paste and put it in Swift because it's not going to work, right? Let's just look at the hypothetical future. So right now in Swift, we already have different ways of declaring bindings. Bindings are basically variables, right? So we can do a let, and that's declaring a binding with a name to a value. A let has the meaning that makes this binding unmutable. You cannot change it. Even though the school, remember, the school is declaring things as variables. So from what the struct itself is concerned, you are able to change things in it. But this specific binding, this name, forbids you from changing it. Instead, if you use var, you can actually change it. You are making a binding that is mutable, a variable. As we have seen, there are other kinds of C keywords that actually are kind of manipulating the binding. The inout keyword, it's kind of like by default you have a let, and we used to have a var, like that had the implicit copy behavior in it. This inout, it's kind of like another binding. It's a binding that lets you reach into the original and actually change it. So it's like a variable without the copy in it. And that's the power of inout. It lets you have a variable that still references the original. So let's pretend that Swift has that. Let's pretend that we can do lets, bars, and now imagine that we can do take the house as an inout variable, right? So we're going here and actually not declaring it as a variable, which will make a copy. We're actually taking as an inout variable. This can have different names like mutable borrow or like whatever you want to call it. And the syntax is probably like you may have to do this to declare it as an inout or whatever, right? Doesn't matter the syntax. Now you have a house that is still referencing the original one. So you can, you know, do anything that you want here to compute the indices, like whatever you want. It doesn't really matter. You have all the power in Swift, but with the addition of that. And now you can just take another one for the student, and this is still keep referencing the original. Here, your mutation, if you print it, it's gonna actually affect the original one. That's what memory ownership can bring us to the table. And that's why I want you to get excited, because you are not gonna longer be forced to do this. You're gonna be able to just write the code that you want, and you just need to know that making it inout, you're gonna start modifying the original one. Let's look at the for loops. How will it look? Well, we already kind of see how by default it's a let, right? But we can make a bar, which is again a mutable copy. But what if we could make a mutable binding that was still referencing the original, that it borrowed the original, allowed you to mutate it, and put it right back? This is hypothetical syntax. Maybe you need to do this, maybe you need to put another keyword here, like, I don't know. But my point is, we can take existing code that works with value semantics, and just by embracing the new ownership stuff that it's coming to Swift, we can actually work kind of like if it was a reference, but with the safety of value semantics. Look at this case. It's exactly the same. What if instead of a bar here in the if let to unwrap the optionals, you could do inout, and now this it's actually pointing to the contents of the optional. You know that optional has none and some has associated value. This inout variable, this inout binding, binds you to the contents in there, if they are there. If not, there is nothing to bind to, right? But then you can mutate it, and you're actually mutating that stuff inside. Another case that is very exciting is the points of origin, right? Like, you could see how we could decide to do different things here based on switching on the enum. And you could have here the, like, I don't know, the name, and you can do stuff with the name. But here, as soon as you want to do something, you can't do that, because again, you're getting a copy. Even if you can do bar here, nothing. But now imagine we have this new power that we can actually do inout reference. And again, maybe we need to do this. I don't know. Now you were able to do a switch, and based on each case, you could take inout bindings to the content of the switch, if that was the case, and actually mutate it in place. This could just simplify so much code, so make it so much nicer, and working with value semantics will be amazing. But now I know what you're thinking. Aren't these just reference semantics then? Why wouldn't you use classes? And my answer is no. No. These are still value types, right? If you take this original and you pass this into some other function and you pass it, it's gonna make a copy, right? Like, these are value semantics. Changing things here, it's not gonna mean changing things there. It's just that the language allows us to make new bindings, new variables that have like a new superpower, a superpower that lets you actually change the original one. And that's where things like memory ownership and the control of lifetimes comes into place, something that is very pervasive in Rust. The thing is that, for example, if you take an inout variable, like if we go here and you have an inout variable, in the same way that the compiler doesn't let you do this because it knows that the binding you made was immutable, you can imagine like that same power, understanding that the binding you did here, it's still kind of like taking control over this original value. So if you had this binding still alive and you wanted to pass it to something else that took this binding, and it was, for example, an inout variable, the compiler will tell you, no, you cannot do that, mate, because you're giving it here, and who knows what's happening here, for example, unless the function made promises, which again, memory ownership, which made promises that says, don't worry, I'm gonna take it, do stuff with it, but it's not gonna escape. I'm not gonna pass it to other threads, I'm not gonna pass it to other objects. So if the promises are made, you can do this. If they are not made, the compiler will tell you, yep, careful here, right? So again, not reference semantics, value semantics with superpowers for mutability. That's how you need to think about this. And that's it. That's what I wanted to tell you. That's what I want you to be excited, and I'm telling you, you should care about memory ownership coming to Swift. Not for the fancy performance stuff, not for the fancy kind of theoretical and language geek side of things. No, but because they gonna have an impact on your day-to-day code. Every time you're using structs, every time you're using arrays, remember, arrays are structs, so you're using structs all the time. Every time you want to change something on an array, you are dealing with this. So imagine that this new functionality is just gonna help with that. How much code you're dealing with arrays? In how much code you are taking indices, because if you want to take the element of the array and change it, that doesn't work. You need to take the index and then set it back again. All of that code cleaned up. Nice. You can take it from the inside of the array, manipulate it, and now magically it's inside of the array manipulated. Super beautiful. So anyway, that was my pitch, for people to get excited about memory ownership in Swift. We were all excited with concurrency, let's get excited with memory ownership. Bit more complicated, some cases are very specific, but this one for me, it's like everybody's gonna be using this. So thank you all for watching. I know I went a little bit, too much repeating stuff that you probably know, but I wanted to get the point across and get you excited about things. So if you have learned something or you enjoyed this, you know what you have to do, right? Thank you all for watching and see you next time.